So, today we'll talk about Bayesian neural networks. Now, Bayesian neural networks are a type of neural networks in which the weights, the biases, and the outputs are in the form of probability distributions. They are not deterministic, as in standard neural networks can be very easily understood from this infographic that the filters we can see the weights and the biases and the outputs, they are in the form of probability distributions. This basically helps us in identifying noise from the data, or if the input is so. Otherwise, in a deterministic sense, if we pass noise to the model, it will give us some output. So to weed out that kind of those kind of results, we basically need Bayesian neural networks. Now there are various methods to do or to make Bayesian neural networks. So the first is Bayes by backprop, which was introduced by Blundell et al. In for learning a probability distribution on the weights of a neural network. The whole of this approach can be summarized as follows. Instead of training a single network, the proposed method trains an ensemble of networks where each network has its weights drawn from a shared learned probability distribution. Unlike other ensemble methods, the method typically only doubles the number of parameters, yet trains an infinite ensemble using unbiased Monte Carlo estimates of the gradients. So this was one. The other one is by using dropouts. So I will go through this blog. This is the third blog of in this video that we will be going through. So how to represent model uncertainty in deep learning. So this has been written by Marco Sagliani. It's a very nice blog. So he starts by saying that everyone who has tried to fit a classification model and checked its performance has faced the problem of verifying not only the KPI like accuracy, precision, and recall, but also how confident the model is in what it says. The most intuitive instrument to use to verify the reliability of prediction is one that looks for the probabilities of various classes. The higher the probabilities, the higher the confidence. This does not imply higher accuracy. It's typical to also have misclassifications with high probabilities. What so basically it's like we have a dog and cat classification example, and in the output we might be having a probability of the network telling us whether it's a dog or whether it's a cat. So those probabilities, they need not imply accuracy. What we do now is to extract the best results from our fitted model, studying the probability distributions and trying to limit mistakes when our neural network is forced to make a decision. We carry out this task in two ways. One, a classical study of probabilities on validation data in order to establish a threshold to avoid misclassification. And second, a recent method based on inference of probabilities based on Bayesian theories with permutation inside a neural network framework known as Monte Carlo Dropout, which provides uncertainty estimation almost for free. So uh, let's say the data that has been taken has 10 monkey species, 10 classes. So it has been divided into the train set and the test set. So we can see these are some of the images. The images are of good quality and balanced amongst classes. We load them with Keras image data generator, performing data augmentation on train. During this process, we store 10% of our train set as validation. This will help us when we'll try to build thresholds on probabilities following a standard approach. According to the scope of this post, we limit the target classes only considering the first five species of monkeys. Okay, so let's say we have this model, the neural network model in Keras, wherein in the input we have the shape is shape plus tuple 3 Okay, so then we have the first we have the convolution max pooling layer, another convolution max pooling layer, and then we have a dropout wherein we are dropping out 50% of the connections. So after training, similarly we have convolution max pool dropout, flattening, and then dense layer and another dropout layer. So we have three dropout layers, and then we have in the output we have a dense layer. So we are using categorical cross entropy, so which is for classification problems, and the Adam optimizer, and the metrics we are using is accuracy. So after training, the accuracy on test is around 0.79, forcing our model to classifies all. Now, uncertainty with standard threshold. The first approach we introduced is based on simple studies of probabilities computed on a validation set. This procedure enables us to know when our neural network fails and the confidences of mistakes for every class. In this way, we create thresholds which we use in conjunction with the final predictions of the model. If the predicted level is below the threshold of the relative class, we refuse to make a prediction. Our validation is composed of 10% of trained images. In order to have an adequate distribution of probabilities to build significant thresholds, we operate data augmentation on validation properly. In a phase of prediction, every image is augmented 100 times. That is 100 more probabilities for every sample. So we'll skip these certain things. And okay, so okay, so coming to uncertainty with Bayesian theory, Bayesian probability theory offers mathematically grounded tools to reason about model uncertainty, but these usually come with a prohibitive computational cost. It is surprising that it is possible to cast recent deep learning tools as Bayesian models without changing anything. The solution is the use of dropout in neural networks as a Bayesian approximation. Specifically, stochastic dropouts are applied after each hidden layer, so the model output can be approximately viewed as a random sample generated from the posterior predictive distribution. So we have the dropout, and these dropouts are basically random, and they are used in the neural network as a Bayesian approximation, and as a result the model uncertainty can be estimated by positional indexes or other statistics taken from the predictions in a few repetitions. So we make a few repetitions with the same input and using the dropout. And let's say if given a new input image, we activate dropout setting it at zero point 0.5. So by default it is turned off by Keras at the end of the training, but let's say we activate dropout and compute the predictions. When we reactivate dropout, we are permuting our neural network structure, making the results also stochastic. It is clear that if we iterate prediction 100 times for each test sample, we will be able to build a distribution of probabilities for every sample in the class. All can be clarified with some colorful plots. So we can very clearly see that different for we get different probabilities for different classes on test images. So let's say the highest probability, the image corresponding to the highest probability is the image that our neural network has actually it's we are calculating an uncertainty estimation, or we are making our neural network as a Bayesian approximation. So we can very clearly see how to construct Bayesian neural networks by simply using two techniques. One was the one was called Bayes by backprop. So basically building a lot of ensemble of networks, and the other is by activating the dropout in in the test in the test predictions. So this was all about Bayesian neural networks. I was really confused for a long time what are Bayesian neural networks and how to construct them. But I used some of 2 3 blogs. I went through a lot of resources, and this is my understanding about constructing the Bayesian neural networks. Thank you so much.